I welcome all the students to the class. Now, since the previous few classes, we have been discussing about the gyroscopic motion, and somehow we have been able to derive the equations of motion of a gyroscope. Okay, certainly we are talking about the kinetics of the rigid body in 3 dimensions. We are trying to do with the force balance and the moment balance of a rigid body in the 3 dimensions. Okay, and the special case that we had was a gyroscope. The reason for taking gyroscope as an example was we had derived the Euler equations of motion, and while deriving the Euler equations of motion, we got into a need of applying the equations. Okay, because as the students of engineering science, it's very important that we should get to know the physical significance of the equations. So Euler equations were derived as the general equations of motion of a rigid body in 3 dimensions, and those equations we applied on a case of motions of a rigid body, what we call as the gyroscope motion. And in the previous class, we derived the equations. We applied Euler equations of motion on a gyroscope and obtained the gyroscope equations of motion. Now, there are some problems that the gyroscope equations of motion does offer to us, which we'll be discussing later on. Very important is to understand the overall, to understand the overall, overall process or overall structure of these gyroscopic equations. But before we discuss the overall structure of the gyroscopic equations, as far as their linearity and non-linearity is concerned, as far as they certainly fall in the classification of the equations, what in mathematics we call as, or what in calculus in particular we call as the differential equations. So certainly we are talking about the differential equations, and we have reached to a stage where we can at least describe the motion of a body in terms of a differential equation. Now, the differential equations, or what we call as the gyroscope equations of motion, are non-linear, and they offer various challenges, the mathematical challenge they offer us as far as their solutions are concerned. Now, before we see these mathematical equations in total, okay, before we see the mathematical challenge that these gyroscopic equations do offer to us, but certainly we will try to model them first to reduce them to a level where we can get physical significances out of them. And later on, we can switch back or return to the base where we have kept all the gyroscopic equations, and we'll see what sort of equations they are. Now, in order to utilize these gyroscopic equations of motion, which we discussed in the last class, today we will be applying them and to two types of motions the gyroscope undergoes. One is what we certainly call as the steady precession. This is a very important motion of the gyroscope, very often encountered in the mechanics, and very celebrated motion as far as the kinetics of rigid bodies is concerned. We talk about the steady precession of a gyroscope. Okay, steady precession is a type of motion the gyroscope undergoes. Now, the question is, what is steady precession? Now, it says the motion in which theta, this is your theta, which we know what theta means. It means the angle of what you call as the angle of nutation. The motion in which theta, the derivative of phi, that is precession, and the derivative of psi, that is spin, remain constant. Okay, also known as steady precession of gyroscope. So in when we talk about the steady precession motion or the steady precession of a gyroscope, okay, that is, we quantize few parameters associated with the gyroscopic motion. Okay, we quantize the angle theta, we quantize the precession, we quantize the spin. That is, we say that the angle theta, the derivative of phi, that is precession, and the derivative of psi, that is spin, these three quantities associated with the gyroscope remain constant. What do they mean? If we return back to our previous figure or the previous picture, look at the parameters associated with the motion of the gyroscope. First of all, we are saying this angle theta. Okay, this is the angle that is associated actually with the inner gimbal. Okay, and the inner gimbal initially in the previous with respect to the reference motion, if we talk about with respect to the reference motion, that's here, this one on the left hand side, this one on the left hand side, this one. Okay, this is the reference motion. Now, if we rotate this inner gimbal with respect to the y-axis. That is, if we happen to rotate this inner gimbal with respect to an axis passing through the BB system, then this inner gimbal will move out of the plane or it will go into the plane as is given on the right hand side. Okay, so what does it mean? It means the inner gimbal is describing some motion, is describing some angle that's called angle theta with respect to the original z-axis or the z-axis of the ground frame of reference. Okay, this theta we have to keep constant, number one. Number two, the derivative of this phi, the derivative of this phi, you know, this phi, what we call as the, the derivative of the phi, we have called this as the precession. Okay, the derivative of this phi, the rate of change of angular motion of this outer gimbal with respect to the z axis. Okay, because what is the angle phi describing actually? Angle phi is describing the rotation of the outer gimbal with respect to the capital Z axis. Fine. The the I will repeat it, that as far as the phi is concerned, the angle phi describes the rotation of the outer gimbal with respect to the z axis or along the z axis. So the question is that we in the gyroscopic precision motion are certainly keeping this constant as well. Okay, the rate of change of this angle is kept constant. That's number two. And the number three is the rate of rotation of this disk. Since this disk is rotating about an axis which is certainly passing through this, like this axis, it's rotating about this axis, and its rate of rotation is certainly its rate of rotation, that is the rate of change of this angle phi, what we have called previously as spin. The spin is also kept constant. So when we describe the gyroscopic motion in which we keep this theta constant, and we keep theta constant, we keep the rate of change of phi, that is precession, and the rate of change of psi, that is spin, as constant, that motion of the gyroscope is known as the steady precession. So when we talk about the steady precession, as we return back to our topic, in the steady precession, we are understanding the motion of the gyroscope in which we are keeping theta constant, in which we are keeping the derivative of phi, that is precession constant, and the derivative of psi, that is spin, as constant. Such a motion of the gyroscope is called the steady precession. Now, how does the steady precision look like? That's something very important and, in fact, very challenging. Now, if we have to realize how this steady precision looks like, you have to visualize the motion of the gyroscope in total. That is, imagine that this disk is rotating about the small z axis. Okay, imagine that this disk is rotating about this z axis with an angular velocity psi dot, and the psi dot is constant. Fine. You imagine, okay, that this disk is rotating about the small z axis with an angular velocity given by psi dot, number one. You also imagine that this entire system is rotating about this capital Z axis, okay, with with an angular velocity such that the angular velocity is given as phi dot. You imagine these motions, okay, and the first motion that we have to imagine is the motion of this disk. Imagine the motion of this disk. What's happening to the disk? The disk is rotating about the small z axis, about this small z axis with an angular velocity. Okay, and how much is the magnitude of the angular velocity? The magnitude of the angular velocity is given as psi dot, constant angular velocity. Okay, number one. Number two is the outer gimbal is also rotating, and it's rotating about the z axis with an angular velocity given by phi dot. Phi dot gives us the angular velocity of this outer gimbal with respect to the z axis. Number two. Number three is in the precession motion. You imagine that the entire system is held, this disk is held in such a way that its axis of rotation is describing a constant angle of theta with respect to the ground frame z axis. These three things we have to imagine. Okay, so what's essentially happening? The outer disk is continuously rotating. The inner disk, sorry, the outer gimbal is rotating with an angular velocity given by phi dot. The inner disk is rotating with a constant angular velocity given as psi dot, and the angle of rotation, the angle that the axis of this disk is describing with the capital Z axis is theta, and theta happens to be constant. Okay, so we are having the motion. The motion is the outer gimbal rotation is possible. Outer gimbal is rotating. Number two is what is rotating is the disk is rotating about the small z axis, the rotating frame of x is z axis, fine. But the angle that is in between these two axes, Eulerian angle between z and z axis is theta, and that happens to be constant. This is the steady precession motion that needs to be visualized as well as imagined. Now, as we talk about the steady precision motion, let's return back to the equations that we already have in hand. The equations that we have are like we were talking about the angular velocity of the disk with respect to the ground. The equation for the angular velocity of this disk with respect to the ground that we are representing by omega from the previous equations was coming out equal minus of phi dot sine theta I cap sine of theta I cap plus theta dot j cap plus theta dot j cap plus psi dot plus phi dot cos theta cos of theta k cap. This is what we had derived previously. And we also derived that the angular momentum of the disk about an axis passing through point O was coming out equal, minus I prime phi dot sine theta I cap sine theta I cap plus I prime theta dot j cap plus I, that's moment of inertia about the z axis, I psi dot plus phi dot cos of theta k cap cos of theta k cap. This is what we had derived previously. And we had also derived the rotation of the rotation of the rotating frame of reference, which we are representing by small x, small y, and small z with respect to the ground frame of reference. Okay, that is the angular velocity of the ground frame of reference. I will write that as angular velocity of the rotating frame of reference. Let me write this as omega r with respect to the ground frame of reference. This is what we had in fact derived previously as well. This was coming out equal to it was minus phi dot. The equation for this was minus phi dot sine theta I cap sine of theta I cap plus theta dot j cap plus theta dot j cap plus phi dot cos theta k cap. This is what these equations we have derived previously, cos of theta k cap. Now, and also, yeah, the summation of all the moments about an axis passing through point O with respect to the ground frame of reference was equal the derivative of the angular momentum defined with respect to the rotating frame of reference, that is small x, small y, small z. This equation we had used previously, plus the cross product between the angular velocity of the rotating frame of reference with respect to the ground frame of reference with h naught. Okay, this is what we had done previously. Now, as we use these equations right now, for the steady precision, what we have for steady precision, our angle theta is constant. Fine. For steady precision, the value of our angle theta happens to be constant. The value of our phi dot is constant. Fine. The value of our phi dot is constant, as well as the value of our psi dot, rate of angular velocity, that's what we call as a spin. This is also constant. Now, as we apply, if this theta is constant, that simply means that theta dot, if theta is an isolated constant, then certainly means the derivative of theta is 0. As we now substitute the value of theta dot to be equal to 0, so here this term goes, fine. So we are losing this term as well, fine. and we are certainly losing this term as well. Fine. So these terms are going. Certainly, we don't have these terms at all. Now, apart from this, as we are assuming these all, this steady precision, our theta dot terms are all equal to zero. As far as this h naught is concerned, the derivative of the angular momentum defined in with respect to the xyz small frame of reference. See, when you have a motion, when you have a steady precision, at that time, the angular momentum of this rigid body remains constant. The angular body of the rigid body remains constant in this configuration when its phi does not change, when its psi does not change, when the angle theta does not change. Its angular momentum is same. Angular momentum means is the angle changing with time? No, certainly the angle does not change with time. Okay, so this term is certainly equal to zero for steady precision. Okay, therefore, if we look at the overall equations, what we obtain, and we make one substitution, that let's suppose that the term that we have here, this psi dot plus phi dot cos theta k cap, we are encountering this term many a times. So we'll make one substitution, that psi dot plus phi dot cos of theta, okay, plus cos of theta. We will keep this equal, we'll write, let this term equal omega. Okay, let's write this as omega z. Now, why we are writing this as omega z? Return back to this equation. You have omega. This is the component of omega along x-axis. This is the component of omega along y-axis. So this certainly has to be the component of omega along z-axis. That's why we are writing this as omega z. Now make these substitutions and return back to the equations, the final equations that we'll obtain. First one will be about omega. As far as the omega is concerned, omega is equal minus phi dot plus omega z k cap. This is for steady precision. Number two term is the angular momentum about an axis passing through point O is equal to minus I prime phi dot sine theta, phi dot sine theta I cap plus I omega z k cap. Fine. This is how it goes. And apart from this, we'll have the angular velocity of the rotating frame of reference with respect to the ground frame of reference. Okay. This term will become for us equal minus phi dot sine theta I cap minus phi dot sine theta I cap along I axis plus phi dot cos theta k cap, cos of theta k cap. Fine, that's it. And now if we return, and the angular momentum, sorry, the summation of all the moments about an axis passing through point O is equal, the summation of all the moments about an axis passing through point O is coming out angular velocity of the rotating frame of reference with respect to the ground frame of reference, and its cross product with the angular momentum h naught defined in the small frame of reference, small x, small y, and small z. If we can open up this, we can certainly write this as, um, we can write this as, to solve this matrices, we can write this as I cap, and beneath I cap, omega rj I component is minus phi dot sine theta, minus phi dot sine theta. Now it's j cap, it does not have a j cap, that is 0. And what's its k cap? Its k cap is, as far as the k cap is concerned, its k cap is phi dot, yeah, phi dot cos theta. That's phi dot cos theta is its k component. Right? Now, what about this h naught? H naught I component is minus I prime, moment of inertia about x-axis, phi dot sine theta. It does not have a j component, that is 0. And its k component is I omega z, where omega z is equal as already described. Now, if we solve it, okay, if we obtain its components, What is, if cross product is done, what is the value of, what is the magnitude of m naught? What is the magnitude of moments about an axis passing through point O? That's equal, the summation of all the moments about an axis passing through point O will come out equal, as we do this term and this term is zero. So we'll only have this, the components along J, because if we take the cross product for the K components, this and this term again will be equal zero. So the components, the magnitude of this cross product will be minus phi dot sine of theta minus phi dot sine of theta I omega z plus I prime phi dot plus I prime phi dot sine theta sine of theta sine of theta and phi dot cos of theta phi dot cos of theta. It will be along j cap. Fine. The reason is we are taking these components for these I, X, Y, and Z, because as you take the I components, so I components are all zero. As you take the J components, that is phi dot sine theta I omega Z, that is here, and minus minus will be plus, that is I prime phi dot into phi dot, that is phi dot sine theta cos theta along J cap. K cap is also equal to 0. That is, we can certainly write this as, this is, since this is second component, this is J component, we have to put it minus, because the first component along I-axis is 0, the second component we start with the minus. So the summation of all the moments will come out to be equal, this will be equal I, we can write this as I omega z, I omega z, I omega z minus I prime phi dot cos theta, and we'll take something common, that is equal phi dot cos, so for, sorry, phi dot sine theta j cap, sine theta j cap. We are not calculating, so this is a little correction here, we're not calculating the magnitude as I was earlier stating, since it's having the direction, this is the total vector. Okay, so the moment of all the forces is given by this form, summation of all the moments is given by this formula. Okay. Now look at the gyroscopic motion. The fact is that as far as this gyroscope is concerned, the gyroscope does not move at all. Okay, there is no translation along x-axis, there is no translation along y-axis, there is no translation along z-axis. The gyroscope is not translating about any of the axes, number one, but it's simply rotating. It is having angle theta with respect to capital Z axis. The disk is spinning, okay, as well as the outer thimble is precessing, okay. So it does have the motion, but all the motions of the gyroscope are rotary motions, not the translatory motions. So we will say for the gyroscope, summation of all the forces acting on it is equal to 0, okay, because the gyroscope does not have a translation motion at all. That's why the summation of all the forces acting on the gyroscope is equal to 0, number one. Number two is we need to highlight two important things about the gyroscopic motion. That's something very important. That is, first of all, as far as the summation of all the moments equation is concerned, we have to particularly explain it in a bit sense. If we return back to the let me first go back to the previous equation. Okay, that's it. Yeah, let me talk about this equation first. This diagram here. We have just now written that the total angular velocity omega is equal to, total angular velocity is equal to, for study precision, it's equal minus phi dot sine theta I cap sine theta I cap plus omega z k cap. We have just written, okay. So it means as far as the total angular velocity of the disk with respect to the ground is concerned, it does have two components. It has a component along x-axis, it has a component along z-axis. When we talk about its component along x-axis, okay, as we talk about its component along that, it is phi dot sine theta, but along negative x-axis. So if we happen to plot it as is being plotted here, if we happen to plot this component of angular velocity of the disk with respect to the ground, okay, and this component, this is positive x-axis, this component will certainly be along negative x-axis, okay, and it has been written here as stated here, this is minus phi dot sine theta I cap, negative of I cap. This is the first component. The second component that it has, it is omega z k cap, okay, it does have a component, and its component along z axis is omega z, and it's along k cap. So this is the component that we have, omega z along k cap, fine. But this omega z that we are writing, fine, it has been written as, okay, yeah, we are talking about this omega z k cap. So we say omega z is along z axis, that is omega z k cap. But we have just written that this omega z is equal to psi dot plus phi dot cos theta, okay, plus phi dot cos theta. Psi dot means, what is psi dot? Okay, and it does have, if you, this is omega z, what we call, this was k cap outside, so we have to multiply everything by k cap. So it was the omega z that we are calling as, the omega z that we are calling as, it's actually phi dot psi dot, and this is a k component as one of the components. So omega z is having the omega z, which we are writing here along z axis. It has one component phi dot along k, phi dot along psi dot along k cap. So that's here, psi dot along k cap. It has one more component certainly along the axis, that is phi dot cos theta k cap. This angle is our theta. Okay, this is whatever is the rotation along z axis, we are writing that as phi dot. So when we write phi cos theta is certainly along the same direction, okay, and this phi k and this psi dot cos theta are all along the z axis. So if you look at the omega z vector from this equation, if you look at the omega z vector, it has two components, minus phi dot sine theta, that is here. It has one more component, omega z k cap, that is here. So by the parallelogram law of vectors, as far as the resultant angular velocity is concerned, this is very, very important. The resultant angular velocity should be along the diagonal of this parallelogram, that is here. This is something very, very important. This equation does tells, it states that whatever be the motion in a steady precision, the gyroscope's theta is constant, the gyroscope's spin is constant, the gyroscope's precision is constant, but for an observer on the ground, fine, for an observer on the ground, the total angular velocity will be along this vector, okay, subtending some angle, okay, subtending some angle, let me call this as angle alpha with respect to the z-axis, and certainly we can even find the value of this angle alpha, okay. The angle alpha is tan perpendicular by base, okay, we can write the tan of this angle alpha is equal, okay, is equal to perpendicular, magnitude of perpendicular is magnitude of perpendicular is it's phi dot sine theta, okay, and the base, its base is omega z, okay. So this formula gives us the angle at which the observer will be watching the motion to be happening. This is the angle at which the motion of the observer, at which the observer will be watching the overall gyroscope to be rotating. So in this class, what we have tried to do, we have just used the gyroscopic equations of motion on a case of motion, what we call as a steady precision. And in steady precision, what we have evaluated for the summation of all the moments about an axis passing through point O. But before that, we first of all inquired about the angular velocity of the disk with respect to the observer on the ground. Number one. As we go ahead, I hope I will be ending up this segment in a quite while from now. I think this diagram I will be explaining in the next class. And hopefully in the next class, I will be talking about one more solution of this equation. That is what we call as the torque-free motion. Okay, but certainly there is something that's very important. The terms that we are coming up that is I need to make you understand is to maintain the gyroscope in precision, the amount of couple that should be applied about an axis perpendicular to the precision axis and to the spin axis of the gyroscope, that I will be hopefully doing in the next class. Thank you.